All right. Let's quickly go through this chapter. This is practical application issues for power semiconductor devices. There are basically three parts of discussion. First is gate drive circuit. The second one is protection of power semiconductor devices, because power semiconductor devices are usually very expensive. So we have taken extra measures to protect these expensive devices. The third one is, in many cases, we have to parallel or seriously connect two or more power semiconductor devices in order to deal with higher voltage or larger current. So these are the three topics that we are going to cover in this chapter. Gate drive, basic function is to generate gate signals to turn on or turn off power semiconductor device according to the commanding signals from the control circuit. This is very easy to understand. There are many other functions of gate drive circuit. Gate drive may provide capability to reduce switching time. Okay. If you have a better designed gate drive circuit, the switching time, especially the turning on process and turning off process, this changing process might be reduced. Okay. And also, if you have a very well designed gate drive circuit, you can also reduce the switching loss. Okay. The power loss during the turning on process and turning off process. You can reduce that so that you improve the efficiency. And third extra function of drive circuit is to supply the improvement on protection and safety of the converter. With better design drive circuit, you can quickly shut down the power converter through the gate drive circuit once you detect there's a failure. There is a overcurrent or over voltage happening in the power converter. So you quickly shut down the power converter in the gate drive. Okay, one thing, and actually this is very important, I want to let you know that gate drive circuits provided by the power semiconductor manufacturers, okay? Many power semiconductor devices manufacturers, they also provide gate drive circuit at the same time. And because they are manufacturing these two things at the same time, they are designing their gate drive circuit to be fitted with the power semiconductor devices they are building. So very often these gate drive circuits are very well designed and optimized. So these gate drive circuits provided by power semiconductor manufacturers are often they are very widely used. Okay. Another very widely used gate drive is in the form of integrated gate drive chips. So in many cases, all these gate drive circuits are integrated into a chip, so that for the user, what you need to do is just buy this chip from the market and connect that with the power semiconductor device. That's okay. So this is very easy to use. So this statement, final statement is on this page is very important. Okay. Gate drive has to also provide isolation between the control and power semiconductor. Okay. You need the isolation. The reason I have already mentioned in the second chapter, because the high voltage and the large current go through the power semiconductor device may destroy the control circuit if you don't have electric isolation between these two. There are two ways to provide isolation. One is optical, the other one is magnetic. Okay? Optical oscillation, one of the most widely used component is called optocoupler. Optocoupler. There is an illustration on the right-hand side of this page. Okay. For example, the left-hand side is control circuit. The right-hand side is the drive circuit you want to connect to the power stage. You want to connect to the power semiconductor device. And this is optocoupler. Okay. The optocoupler is actually consisting of two things. One is a LED inside. The other one is a phototransistor. Okay. So once you have current flowing through this LED, then you are generating lights inside this optocoupler, and these lights shed it on the base area of this phototransistor that will be equivalent to generating a base current, generating base current for the transistor. So once you have base current, originally there's no current flowing through, and therefore the voltage between this point and this point will be high level. Okay? And therefore, when you have base current flowing, then that means the voltage between these two terminals will be dropped to low level. Okay? So that is the way to generate signals, generate control signals, or transfer control signals through optocoupler. Okay? So basically there are two ways, magnetic, optical. Magnetic is very usual way. Okay, there are, in the following parts, there is a discussion about the different drive circuit for thyristors, for GTOs, for MOSFET, and for IGBTs. I will not get into details. You read through the textbook, both in the Chinese textbook and the English textbook. There's a good portion of the textbook discussing about that. So you always have a requirement. What kind of requirement for the gate current, or what kind of requirement for the gate voltage? For current-driven device like thyristor and GTO, then you always talk about the what kind of waveform you require for the gate drive current. Okay, this is the example for thyristor. Then you usually need this waveform of this shape of waveform for gate drive current. You have a very stronger leading part. Okay, and this width of this triggering pulse might be longer long to some extent. So there's also very detailed requirement on that. I will not get into details. This is the typical example of gate drive circuit for thyristor. This is transformer isolated. Okay, there's a transformer to provide isolation. And there's another example showing the gate drive circuit for GTO, because GTO is also current driven. So you can see here the gate current here also has a very special requirement. Have a special shape of waveform we require for the gate current. Gate drive circuit for power MOSFET and IGBT, I don't want to get into details. Protection. We have mentioned that because power semiconductor devices are really very expensive, then we need extra protection for these devices. Usually you should have over voltage protection and over current protection. Okay? Over voltage, over current. Okay, and we can also have another type of protection circuit which is called snubber circuit. Snubber circuit. Snubber circuit is provide a specific protection that can limit the voltage changing rate or current changing rate and reshape the voltage or current waveform during the switching process. Okay, this is a snubber. Snubber is basically providing an extra protection for limiting voltage changing rate du dt or current changing rate di dt, and reshape the voltage or current waveform during the switching process. Okay. Over voltage, many reasons could cause over voltage. Okay. I will not go through the details. Let's see, there is external reasons, I mean outside of power converters, and there is also internal reasons inside power converters. The over voltage could be caused by the operation of mechanical switch in the power system. When there's a circuit breaker turns on or turns off, then that operation may cause over voltage across the power converter. And when there's a lightning, pay attention, lightning is different from lighting. Lightning, those two are different things. Lightning. Okay. Thunder. And lightning. When the transmission line or distribution line is caught by a lightning, the lightning, let's say, hit the transmission line or the distribution line, that will also cause a lot of energy, a lot of transient energy across the transmission line or distribution line, and therefore that will cause also over voltage. So that's the another typical reason of over voltage. From the internal side, inside the power converter, there are also many reasons that could cause over voltage. One is, let's say, over voltage caused by turning off process of a fully controlled device. For example, IGBT or power MOSFET, when this power MOSFET or IGBT is turned off, then originally there is current flowing through, and suddenly this current is turned off. And this is a very high DIDT. There is very high current changing. This very high current changing will be causing over voltage because, okay, for example, if this is IGBT, okay, originally there is current flowing here, and suddenly I'm turning this off, then I have very high DIDT. And then this inductance, the equivalent inductance of the wire, okay, you always have some wire connecting this IGBT with other circuit. So this equivalent, let me use LP, parasitic inductance of the wire. Because of the DIDT multiplied by this parasitic inductance, that is very high value. Could be LP multiplied by DIDT. So when you turn off this IGBT, there's a sudden change of current, very high DIDT, multiplied by this inductance, that will be very high voltage. That voltage will be generated across this IGBT device. Okay, that is one typical reason. Another typical reason is reverse recovery of diode or thyristor. If you still remember, for the diode, the reverse recovery waveform will be something like this. Originally, the current is flowing, the positive current is flowing through the diode, and when you turn it off, let's see, you apply reverse voltage across the diode, that current will be decreasing to 0, and it will not be stopped at 0. It will be changing to reverse direction, and then coming to the reverse peak and suddenly coming back to 0. This is the reverse recovery current for the diode. And for thyristor, this is also similar. When you turn off thyristor, that current flowing through thyristor will also be first decreased to 0 and then going to the reverse direction. This part is called reverse recovery current. Okay, reverse recovery current. And there's always this sudden change from the reverse peak back to the 0. This process, this is a very high DIDT. When you have this high DIDT, similarly, so let's see, when you have IGBT or power MOSFET is always connected with anti-parallel diode, in many cases. So when originally there is current flowing through this diode, and suddenly you are turning this diode off, so the current flowing through here will be in this direction decreased to 0, and then it will be changing direction. There will be reverse current flowing, coming to the peak, and suddenly come back to 0. So there will be current flowing this way and suddenly stopped. That is also very high DIDT. And that high DIDT, together with this wire parasitic inductance, will also cause high voltage. Okay. That high voltage will be generated across this, let's see, the anti-parallel connected IGBT or power MOSFET. Okay. Those are the two basic reasons for internal causes of overvoltage. Okay? There are many measures we can take to deal with overvoltage, and this is a figure showing all different measures and positions. Okay, we can use lightning arrestor. Lightning arrestor. Okay, we can use capacitor with resistor, because we know capacitor is usually used to absorb overvoltage energy. Okay, because capacitor tends to maintain the voltage across the capacitor constant. Okay, so you can use RC or RCD. D means diode. So resistor, capacitor, diode can be used together. So that because of the diode, I can absorb one direction voltage, but for the other direction, I do not care. So you can use many other nonlinear devices. Okay? All these things I'm listing here are nonlinear devices. Zener diode, metal oxide varistor, metal oxide, varistor, okay, breaking over diode. All these things are nonlinear. Nonlinear means when the voltage across this device is within the normal range, then this is acting like linear component. Nothing happens. But when the voltage across this component is higher than a certain value, then this device will be acting like a short circuit resistor. So the energy caused by this overvoltage will all be dissipated on this nonlinear components. Okay, I will not get into details. So many nonlinear components you can choose to deal with that. Okay, overcurrent. That is easy to understand. In many cases, the current flowing through the power converter or flowing through a semiconductor device might be exceeding the sustainable range. Then we have to take measures to deal with that overcurrent. We can use, these are the measures we can take to deal with overcurrent. You can use fuse. This is often used not only for power converters but also for many other electric power equipment. Fuse. This is a very informal name of fuse in Chinese. Okay. And then you can have circuit breaker. Circuit breaker. Circuit breaker. In the School of Electrical Engineering, we have a division which is called electric apparatus and switch gears. Electric apparator and switch gears. Electric apparatus, switch gears. They are basically talking about circuit breakers. This switch gears means circuit breakers. High voltage circuit breakers or low voltage circuit breakers. Okay, so we can use circuit breaker to protect. Once there is overcurrent happening, and then we turn off the circuit breaker, trip off the circuit breaker so that this current will be limited. Okay, that's the second measure. We can use control. Okay, we have learned feedback control. And we can measure the actual current we want to control. And once that current is exceeding the level we can accept, then we shut off the power converter or use the controller to regulate this current to be maintained in the appropriate range. Okay, so that's the third measure. We can use current feedback control to control the value of current. And this feedback control can also be applied to a gate drive. Okay, you can measure the actual current flowing through a power semiconductor device, and once that current is exceeding this appropriate level, then I can quickly shut off the gate drive circuit. The gate drive will send out a turning off signal to the power semiconductor device and turn off this device. Okay, so these are the different measures we can take to protect power semiconductor device. Of course, the measures you take in the gate drive is the fastest measure you can take. Once you detect this overcurrent, you shut off it. That's the fastest you can take. Okay, and this measure you can take in the feedback control system is also very quick. And usually circuit breaker and fuse, these are slower measures because those are mechanic things. Circuit breaker is usually mechanic switch, and it takes time to be performing the function. Okay, and the fuse is takes even more time because the principle of fuse is really based on thermal trip-off. When the current going through this fuse is exceeding a certain level, and then the heat generated by that current will cause the trip-off of this fuse. And you know, always it takes time for this heat to actually be accumulated and trip off the fuse. Okay, I will not go into details. A lot of measures you can find out. For snubbers, okay, I can take some time to look at that. Let's see, I will not get into this detail, but I'll just go through this picture here, the basic operation principle. Okay. This is a turn-off snubber. That means this snubber can be used to deal with high overvoltage when you turn off this IGBT, let's say. So remember, as I said, there is always a parasitic inductance because of the wire. Okay, there's a wire or structure. And this is the parasitic inductance. Let's say this is Li. So when you, if you don't have this turn-off snubber, then when you turn off this switch, turn off this IGBT, the current flowing through this IGBT and this inductor will be suddenly changing from a certain value to 0. So that is a very high DIDT. That high DIDT multiplied by this inductance will cause overvoltage. Okay? So in order to deal with that, I can parallelly connect this part of the circuit with the IGBT. This is just a resistor, capacitor, and diode. So when this is turned off, this overvoltage will be absorbed by this capacitor. Okay? The current, the energy stored in this parasitic inductor can be flowing through here. The energy is stored by these parasitic inductors, this current. When this switch is turned off, it will be flowing through, first through this diode, because its equivalent resistance of diode is very small. Okay, the current will be going through this way. And therefore, the energy that originally could cause overvoltage, that energy now will be absorbed by this capacitor. Okay, absorbed by this capacitor. Okay, that is called turn-off snubber. This is the way to absorb overvoltage. Okay, somebody may ask, what happens when about this energy stored in the capacitor? This energy will be, next time when this IGBT is turned on, when this is turned on, this energy will be dissipated through this resistor. Okay? The current will be flowing this way. The energy stored in the capacitor will be dissipated through this resistor and released through this IGBT in this way, when this IGBT is turned on. Okay? Yes? Okay, his question is, the reason we want to turn off IGBT is that we want to have this current stop flowing this way. So once we have this, let's see, once we have this snubber circuit, then there will be still current flowing. That's not what we want. Okay, that's correct. But we have to deal with this. Because there's always energy, because you have this, always have this parasitic inductance. Parasitic inductance. He's right. Okay? If we don't have this parasitic inductance, then there's no problem. Okay? We don't need this knobber. When we turn off this IGBT, then the current will be turned off. But in practical applications, there's always this, you have always this wire there. This IGBT has to be connected with other components through wire. Okay? And once you have a wire, a section of wire, then you have this inductance. Okay? And when you have this parasitic inductance, then every time when you turn on the switch, turn on IGBT, there will be current flowing through IGBT. There will also be current flowing through this parasitic inductance. That means there is always energy stored in that parasitic inductance. So when you turn off this IGBT, the energy stored in this parasitic inductance has to be dealt with. You have to deal with that part of energy. Otherwise, these components cannot be operating correctly. So we have to release that part of energy. Okay? So that energy has to be dealt with. The way I do this is use this snubber circuit so that that energy will be released over here, stored in this capacitor first, and in the future once this IGBT is turned on again, I release that energy through and dissipate it through this IGBT and dissipate it on this resistor. So it's not what we want, is that we have to deal with this. We have to deal with this energy. Okay, that's turn off snubber. Similarly, there's turn on snubber. Okay, remember this parasitic inductance? When I turn on IGBT, this inductance is actually good. This parasitic inductance is good for us. Why? Because when I turn on IGBT, because of this inductance, the current flowing through this IGBT cannot be increased suddenly. Okay? There's always a limiting. This inductor can always limit this dIdt. Because when this dIdt is too large, this is not good for IGBT. So this inductor is actually acting like a turn-on snubber. Okay. That's the way we want. We want this turn-on snubber to be dealing with this over voltage and over dIdt, over dIdt, over the DUDT. So that way, on the right-hand side, we actually are changing the waveform of the voltage and current during the turn-on or turn-off process. You can see on the upper right level, you can see this dashed line here is the waveform when we don't have snubbers. Okay? When I turn on the switch, the current will be increased quickly. When I turn off the IGBT, the voltage across the switch will be increased quickly and exceeding a certain level. But once you have snubber, the turning off process will be slower because of that capacitor, and also that over voltage is smaller. Okay. Energy will be mainly absorbed by the capacitor. And turning on process is also slower because of that inductor. Okay? So that way we change the shape of waveform during the turning on, turning off process. This is good for the safety operation of IGBT. And this also helps to reduce the switching loss. Okay? You can see on the bottom right-hand side, I'm listing the voltage and current switching trajectory. Without turn-off snubber, during the turning off process. Without turn off snubber, the voltage across this IGBT will be increasing, but the current does not change, the current increasing, and then current decrease. It will be going along this path. But once you have turn off snubber, the voltage will be increasing slowly. The current will be decreasing first, and then voltage increasing. So go along this curve. This curve, you can see, is going along this low current, low voltage area. So the energy loss along this curve is much less than energy loss along this curve. So actually this snubber also helps to achieve lower energy loss during the turning on, turning off process. Okay. There's also a lot of discussion in the lecture notes or in the textbook. So you read through that after the class. Okay. Parallel and series connection power devices. This is very useful when a single device cannot deal with large current or large voltage, high voltage. So when you need to deal with higher voltage, you seriously connect several devices to deal with high voltage. When you need to deal with large current, you parallel connect several devices. But there's always an issue. This issue is when you series connect devices, you have to deal with what we call even voltage sharing. Voltage sharing. Voltage sharing. So you have to make sure all these seriously connected devices, they are sharing this relatively same amount of voltage. If one device is taking too much voltage, that device will be destroyed. Okay. Once this device is destroyed, let's see, do I have a picture here? Yes. I'm connecting two thyristors together in series. Okay. If this thyristor is taking too much voltage, then this thyristor will be destroyed. Once this is destroyed, all the voltage will be applied to this one. This one will also be destroyed. Okay. So we have to make sure the total voltage is evenly shared among each individual device. So that's the major issue we have to deal with. Okay? So for series connection, we always have to pay attention to, you have to take measures to make sure voltage are evenly shared among these seriously connected devices. And then for parallel, similarly, for parallel connection, you have to make sure the current would be evenly shared. Otherwise, if one device is taking too much current, that device will be destroyed. Once that is destroyed, all the current will be flowing through other device, and this will also be exceeding the sustainable range, and those devices will also be destroyed, possibly. So for parallel connection, you have to deal with the current sharing, evenly current sharing. So those are the two issues you have to pay attention to. You have to take measures to do that. I will not get into details. That's probably the things I want to cover in this chapter. Let's briefly make a review of the course. So we basically covered everything almost, but now once we have all this knowledge and basic understanding of power semiconductor devices, power converters, control techniques, and even some applications, now probably we can have a better understanding of what we have mentioned in the first class. Okay, this is going to be very interesting. We can very easily understand that power electronics is the electronics applied to the conversion and control of electric power. Okay, and that power range could be as small as milliwatts, but it could be as high as gigawatts. Okay, And a more exact explanation of power electronics is that the primary task of power electronics is to process and control the flow of electric energy by supplying voltages and currents in a form that is optimally suited for user. Okay. Power converter is actually doing things, the objective of power converters is actually supplying to the user with suitable voltage and suitable current. Okay. That's the basic function. This is easy to understand now. Okay. Power converters can be classified into this different types based on the different types of electric power. Okay. For DC power, we can change the magnitude. For AC power, we can change frequency, we can change magnitude, we can change number of phases. Okay. Single phase to three phase or three phase to single phase. And therefore, we can classify power converters into four types. AC to DC, AC to AC, DC to DC, DC to AC. And then we have special names for all these four different types of power converters. Okay? So these are easy to understand. Okay? And then this power electronic system will be in this way. We have a power converter, we have a control circuit. This control circuit is actually sending out gate signals to control the power semiconductor devices in the power converters. This will be based on what kind of commanding signal you have and based on the measurements from the input and output side. Okay? That's what we call power electronic system. We make this system in this way. Okay? And the input side, the source part is maybe electric utility, it may be coming from battery, maybe other energy source, and maybe coming from another power converter. For the load, it might be a motor, electric motor, it might be a lamp, okay? It might be a heating equipment, it might be another power converter also. Okay? And the task of power electronics has been recently extended to also ensuring the currents and power consumed by power converters. Okay? Originally, power converters used to supply the most suitable voltage and current for the load. Now power converters is also used to make sure the input power this converter consumed is also in a good form. For example, we also talk about how to make sure this current we absorbed from the source is a sine wave, has smaller harmonics. Okay? We also talk about how to make sure the reactive power we absorbed from the utility grid is very well controlled. Okay? So this we can understand that now. Okay? This is easy to understand now. The relationship with information electronics, the relationship of power electronics with power, with electronics, with control is now very clear. Okay? And the power electronics relationship with other disciplines now very clear. So electric power is now used almost in every aspect and everywhere of modern human society because electric power is the major form of energy that we use in modern human society. Okay? And power electronics objective is exactly regarding how to use electric power and how to use it effectively and efficiently and how to improve the quality and utilization of electric power. Okay? Now this is all very clear. Power electronics and information electronics, this makes two poles of modern human society. These two are very important. Information electronics is just like a human body, a human's head, mind. Power electronics is just like a human's muscle and bones. Power electronics is providing energy. Okay? And the history of power electronics is now also very clear. The thread of power electronics history precisely follows and matches the breakthrough of power devices. Once you have better devices, power electronics is evolving to another stage. In 1957, when thyristor is invented, it enters into the first phase. When these fully controllable devices were invented in 1970s, it entered into second phase, GTO, GTR, power MOSFET, okay, those were invented during that phase. So in the 1980s, when IGBT was invented and coming out, then it comes to another phase of power electronics development. Okay, there's a discussion about that. Okay, IGBT, power MOSFET, resistor, and also not only in the power device but also the controller circuit. Before 1980s, people were still using microprocessor, microcomputers, and after 1980s, most people now are using a better controller chip like DSP, digital signal processor. This is a much better, much stronger, even powerful, more powerful microcomputers. So you enter into a new stage. Okay, now you can understand all these applications, why these applications need power converters. Okay, so I will not go through that part. Okay, so the basic trend is that it is estimated that in developed countries now 60% of electric energy goes through some kind of power converters before it's finally used. And power electronics has been the major contributions to a better performance power supplies and better control of electric equipment. It can be providing energy saving and environment protection. Okay, so I will not go through that. Okay, then there's also I would suggest in chapter 2, there's also a part talking about the future development of power semiconductor devices. I would suggest you go through that part after the class. Okay, let's see which part is that. Section 2.5 and 2.6. 2.5 and 2.6. Those two sections are actually providing you with some materials that describes the current trends or current development of power semiconductor devices. As we said, the developing of power electronics is always coming along with the development of new devices. In those two sections, there is some material talking about what are the new devices we're developing. It's not currently available, but we're developing new devices, 2.5 to 2.6. Especially the part talking about power devices based on new material, silicon carbide, okay, material. Silicon carbide. So far, most of our power devices are based on silicon. Okay? Using silicon carbide, this is called wide bandgap material. This will give us much better performance. Okay? So pay attention to that part. That is the trend. So in next 10 or 20 years, all these new material device will give us much better performance. Okay? And that's it. What I want to review the course. I know many of you want me to talk about the final exam, right? My suggestion is that you go through the material of the whole course based on these lecture notes. That's my suggestion. Because this lecture notes is basically covering it's basically giving you a outline, all the outline of the material. Okay, you can find out almost all the major issues, solutions on this lecture notes. Okay, so you go through, when you do the review of the course, you go through these lecture notes. Okay, when you come to a point you cannot understand it very well, and you go to the textbook to find out the answer. Okay, the final exam will be don't be worried about that. It will be very simple. Okay, it will be relatively at the same level difficulty as your homework. Okay? So if you are okay with doing your homework, then everything will be okay. Let's see what else. For the let's say for the power semiconductor chapter, that's chapter 2. As I said, basically we will be focused on four devices, 4 types of devices. Remember, diode, thyristor, those are the 2 basics. Okay, and then power MOSFET and IGBTs. Okay, focus on those 4 types. Others don't care about that, okay, because we no longer use those devices. Right now we are only use these 4 types. Okay, and you have to make sure that look at the different devices. So which one is able to handle the largest power? Which one is to be able to switch at the highest frequency? Okay, that's the semiconductor chapter. Okay, and the rectifier, you should be focused on single-phase bridge, the 3-phase bridge. Single-phase full bridge, 3-phase full bridge. Okay. That's the requirement. Okay, and what else? DC to AC. DC to AC, mainly focused on voltage source inverter. Okay. Single phase bridge, 3-phase bridge. Those are the 2 most widely used inverters, voltage source inverters. Okay, and then DC to DC. For DC to DC, we have several basic power converters. Okay. Buck, boost, buck boost, and choke. These 4 are the major ones you have to be pay attention to. Okay. And isolated DC to DC. Isolated DC to DC, we really do not get into details. What you need to do is understand all these different types of isolated DC to DC, different names. What are the circuit structure of these different isolated DC, like forward converter, flyback, okay, push-pull. What else? Half bridge, full bridge. Those are the basic structures we mentioned for isolated DC to DC. AC to AC, okay, we will be focused on different control methods. Okay, for AC controllers, we have 4 different control methods. Okay, for frequency converter, we also have 2 different methods, control methods. We usually do not get into details of operation for AC to AC. Usually, we do not get into details. So you just know the basic ideas of AC to AC, what types we're using, what kind of different control methods we're using. Okay, that's AC to AC. And then PWM, that's a key part. Okay, what is the operation principle of PWM? What are the major PWM techniques? Triangular wave sampling, that's the major one. Space vector, SVM is not required as a final exam, in the final exam. SVM is too complicated. Okay. What else? Soft switching. Soft switching is just basic idea. What is soft switching? And what are the purpose of doing soft switching? Okay, those are basic ideas. Okay, Different forms of problems in the final exam. There might be a calculation, okay? As I mentioned, there might be some calculation, but the calculations will be basically in the AC to DC converter, rectifiers, and in DC to DC. Okay? For those two parts, we will have some calculation problems there. You just go through the homework. If you are able to do the homework by yourself for those calculation problems, then you are okay. You're okay to do this about this calculation side. Okay. Then basically it's just questions. Okay. Brief answers to all these questions. Then, in this case, this lecture notes is very good. Okay. We always list the basic ideas of the important points of some questions. Okay. What else you want to know? We already overused almost 5 minutes. What else you want to know? A time? I know there are other classes they have not completed. So our idea is probably put this date of final exam to after the new year, to be after the new year. Right? January, right. First week, I would like to put that in the first week of January. That's,
filling the blanks and multiple choice.
yeah, we do have that. We do have filling the blanks. Okay. We don't have multiple choice. Just single choice. Okay. Filling the blanks. That one we do have. That's. Pardon me?
Any long question?
No, it's just short questions. Okay. Short question. You have to answer those questions based on basic ideas. As long as you can answer some basic points, that will be okay. So you can see it's not so difficult. What? Pardon me?
2 hours.
2 hours is surely. Is it 2 hours or 2.5 hours? 2.5. Okay, 2.5. You are not allowed to bring any vocabulary. Okay? Use your own minds. Pardon me?
Can we negotiate the time?
Negotiate what time?
Because someone thinks it's too late
Well, we can still discuss about that, but I'm afraid because other classes, they prefer to do that test.
we don't have a schedule now. So
Yes, we can discuss that. I agree. But I'm afraid that the final result is still the first week of January. I'm afraid that. We still have, let's see, we'll arrange some office hours before the final exam, okay? I'll let you know, okay? Office hours, and you can come to our office and discuss with me. Any other questions? So the basic requirement is that if you still remember, for each major power converters I mentioned, you have to be able to analyze this power converter. Okay? You have to be able to understand what is the operation principle. What do I mean by operation principle? When the switch is turned on, how the current is flowing, okay? How the energy is transferred from where to where. Okay? What are the voltage waveforms and current waveforms at different points? These are the basic requirements. Okay? And you should also be able to draw the circuit diagram. You should be able to draw the waveforms, current waveform, voltage waveform, and even the control signals. Okay? How do you control the gate? What are the control signals you send to the power semiconductors to make sure the circuit is operating right? Okay? These are the very basic things. You have to be understanding that very well. Calculation, as I mentioned, is just in AC to DC converter and DC to DC, so for only those parts. We don't have extra requirements for calculation for other power converters. Okay? So always follow lecture notes. So if anyone who is not attending this, who has been absent for this class, for this course, for many times, is probably not good for getting a good score in the final examination. And don't take, be serious about the final exam, but don't be too much stressed, too much stressed. Remember, we already have 40 points, right? 40% of your performance is based on homework, okay? Based on the in-class test, based on your performance in the lab, and based on performance in the class, okay? We already have 40%. The final exam is only 60%, okay? So if any further questions, you can come to my office, okay? Today I'm still be in my office for the class 3 and 4, okay, in my office. You are very welcome to come to my office and talk to me. And you will have plenty of time to prepare for the final exam, and hope every one of you have a good score in that final exam. All right. So class dismissed.